Chapter 7 and 8, Section 1, Part 2. So in this part, we will have two techniques for generating pseudo-random numbers. They are linear congruential method and combined linear congruential generators. Okay. There are a lot of random number generator methods in the literature. So let's see what are the criteria in order to compare those methods. The first one is the method should be fast. So yeah, the method should be computationally effective because if it's not fast, then it will take time in the simulation run. So we'll have a longer run time for the simulation models. And the second criteria here is having a sufficient long cycle. So what's uh, the meaning of the long, I mean the cycle? The cycle here is the length of the period that we are repeating the sequence of randomly generated methods in previously. So yeah, if we generate a sequence of random numbers and then after a while that sequence is started to be repeated, then that length of the period is called cycle. Okay. And in a special case of cycling, we have the degenerating. Yeah, I mean, if we have a random number generator method that uh, the length of the cycle is too short and the random numbers are repeating actually over the time, then that's not definitely a good random number generator method. Okay, and so the random numbers should be repeatable under some conditions and given the same point at the start, because without this, we can't debug the methods or we can't compare actually the different methods. But here, I mean, this repeatability is not meaning that that random number generator method is not a good one, because yeah, they should be repeatable, but after a very long cycle. Okay. And the last one, I mean, here is that two main properties that we had before. I mean, any random number generator method should have the two properties of uniformity and independence. Okay. Let's start the first method, which is a linear congruential method. Here we generate a sequence of integers x1, x2 between 0 and minus 1, m minus 1. And then if we divide any of these integers by m, that will be the random number, Ri. Okay, so here xi plus 1 will be calculated based on the xi, the previous number, by this relation, a times xi plus c mod m. Okay, so here the mod is the modulo, and this function returns the remainder of dividing axi plus c by m. Okay, so here if we start from I equals 0, then x0 is called seed of this random number generator. A is a multiplier, c is an increment, and the m here is the modulo. Okay, so the modulus function or the mod function here uh, will return the remainder of dividing axi plus c by m. Okay, and then if we divide the integers generated, let's say xi by m, we will have a random number, which is Ri here. Okay, so let's have an example here. For example, x0 is 27, a equals 17, c equals 43, and m equals 100, right? So x1, the first one, will be ax0 plus c mod m, right? So x1 will be 17 times 27 plus 43 mod 100. Okay, and here this number is 502 mod 100, and so if we divide 502 by 100, the remainder will be 2, right? So x1 becomes 2, the number that we have right here. Okay, and now if we continue calculation, x2 will be a is 17 times x1, which is 2 here, plus 43, and then take the mod with 100, then this number will be 77. Since it's less than 100, then the remainder will be 77, right? So yeah, here we have x2 as 77. Okay, so yeah, it's so easy. We do the calculation based on this relationship that we have here, and after calculating the xi's, the integers, we divide them by the m, and then we will have the random number. Okay, and the cycle is the length from the beginning when to when a value r appears again, right? So if we take a look at this example, we see that we see that the first random number generator is 0.02, and then the fifth one again is 0.02. And if we continue, we'll see every 5 numbers we are actually repeating the numbers. So here in this example, the cycle is 5. I mean, the length of the period that we have repeated random numbers is 5 in this example. Okay, you might try this another example in Excel by having the x0, the seed, as 7, and then a, the multiplier, as 5, and c as 4, and then m as 16, and you'll see there that the length of the cycle will be longer than this example. Okay. So the first concern on this method is having discrete random numbers instead of continuous over 0 to 1. Okay, so why we are saying this? Because if we consider this method, xi plus 1 equals a xi plus c mod m, right? So the remainder of dividing a xi plus c by m could be any number of these, 1, 2, 3, up to m minus 1, right? So the random numbers could be these numbers, right? 1 over m, 2 over m, 3 over m, up to m minus 1 over m, right? So as you see here, we have a discrete set for the random number instead of having a continuous set. So what can we do here is considering a very large number for m. Then by having a very large number for m, this concerns will be a little concern, actually, little consequence, actually. So for example, we can assume that m could be 2 to the power of 31 minus 1, or m to the power of 2 to the power of 48. These two actually numbers are very common in the simulation packages. The second consideration here is the cycle length. So we know that the longer the better, right? So and I think we can figure out by having some examples in Excel that selection of the parameters, I mean a, c, m, and x0, drastically affects the properties of the method. I mean, the cycle length is actually impacted by these parameters. So the higher m value will lead us to a longer cycle length. Okay, so and also we should be careful about choosing x0, the seed, and then the increment and the multiplier. Okay, so for example, if we choose m a power of 2, say 2 to the power of 31 minus 1, which is this number, and this is a prime number actually. And then if we consider c, the increment as 0, and a as 7 to the power of 5, this number, then the longest possible period, which is m minus 1 over 2 billion, will be achieved. Okay, so yeah, as you see here, we need to play with the value of the parameters, or we need another method in order to optimize. Let's say I'm not optimize, just let's say maximize the cycle length of this method by choosing the right values for the parameters. Okay, the random numbers generated by the linear congressional method are called pseudo random numbers. Okay, so we expect to have these properties for any random number generator method. As we talked before, the primary properties are uniformity and independence, and the secondary properties are maximum density and maximum period. So maximum period is about the cycle length, and we know that the longer the better. And the maximum density here is about the gap. If we generate a sequence of random numbers, then there shouldn't be a large gap in 0 to 1. So this guarantees actually having the density, the maximum density of that method. Okay, and the variants that we have for the linear congressional method can be these two. If we have a non-zero increment c, then our method is called mixed congressional method, and if we assume the increment has 0, then that method is called multiplicative congressional method. Okay, the second method that we have here is combined linear congressional method. In this method, actually, we combine two or more multiplicative congressional generators. So here we assume that we have k different congressional generators, and if we generate the integers of these methods, so we'll have k xi, right? So here we have xij, and j is the index for the kth integer. Okay, so if then we combine these k integers in this relationship, as you see here, and then take the modulus of the combined integers as one integer number with m1 minus 1. Okay, and that will be our xi here. Okay, and then the random number will be, if the xi is a positive number, we divide that xi by m1 in order to obtain the ri, the ith random number. But if xi equals 0, then we consider m1 minus 1 divided by m1 as the random number. And as you see here, the maximum period this method can generate is this number, which is a very large number. So yeah, this is actually the point of this method. By combining the linear congressional generators, we can increase the length of the cycle. Okay, so here we have an example. We have two congressional methods, k equals 2, and we have the parameters here. Okay, so in the combined congressional method, the xi is here, since we have just two methods, so
we'll have sum over j going from 1 to 2 minus 1 to the power of j minus 1 xi j, and then taking the modulus with the m1 minus 1, right? So as see here, if we consider j equals 1 and j equals 2, then here we will have minus 1 to the power of 0 x I1, and then plus minus 1 to the power of 1 x I2, right? So here it will be x I1 plus actually not plus, minus, actually here it minus 1 to the power of 1 becomes a negative number, so minus xi2, right? So as see here, we may end up with a negative number for xi. In this case, we can increase the first element xi1 by a multiple of xi2. So in general, if we have, let's say, a modulus b, and then the result is a negative number, I mean the remainder is a negative number, then we'll have this. We can increase a by multiples of b, okay? And then modulus b, the result of these two are exactly the same, okay? So yeah, here we need to consider this method, because for some numbers we may have negative numbers, and then we increase that negative number by a multiple of the second number, and then by having that we'll have a positive number at the end for xi, and then the rest actually is simple and based on the method of the combined linear congressional method. Okay, so yeah, you can easily calculate these numbers in Excel by having this rule. Okay, so this was the second method, and in the next section next week we will see the test methods, that how we can test if a congressional, if a random number generator method is working well and having those two main properties. Okay, thank you.